Hello everyone, welcome to the class ECE317, the digital signal processing. Today we will do the review for the final exam. Actually this is I can say this is the last class with lecture of this semester. Then the next week we will have some just for questions, the class for questions. Alright, this is a ECE317 14th week Friday's class. Okay, this is really the last class with lectures. Okay. These lectures for the review for the final. Review for the final. And when is the final? Actually, I gave it on Monday, right? We already have it in the Monday. Final exam. It will be Friday. Friday 10 to 10:30 or 10. 10:30, right? 10:30 to 12:30. Friday it will be which day? May 7th, right? May 7th. Yeah. Okay, so this is the final exam. And how it works, similar with the midterm exam. I will post the problem in the Blackboard. I will also send the problem to you by email at this time, and then you work. After you're done, you upload it to the Blackboard. Upload it to Blackboard. You have 30 more minutes for the upload, right? And about the exam, what can we say? Okay, this is 2 hours, right? We have 2 hours time, so 2 hours with 6 problems. 6 problems. Okay. Yeah, midterm we have 4 problems. Now we have more. We have 6 problems. The problem is also similar, and I will have a sample problem in the Blackboard, and what else? Yeah, I suggest you prepare a formula sheet. You prepare a formula sheet. Okay, so yeah, in general just like this. Okay, then the next week, right? This week this is the last class. The next week we do not have class. In the 15th week we do not have class, but we have Zoom meeting. For questions. That will be in the 15th week. There will be, let me see, we have Monday, Wednesday, Friday. The class time, there will be 10 to 11 a.m. This is our class time, right? And also we have an office hour. That is which day is our office hour? It's Wednesday. 4 to 5. So in the 15th week we have 1, 2, 3, 4 question types. You can say they are already office hours. You can bring any problem during your review. You go to here, then we can meet in the Zoom. We can discuss the problems. You can also go to the office hour of TAs. They will have just as a normal time. You check the Blackboard, you can find the TA's office hours. So you can also go to TA's office hours. And then we have the 15th week. In the 15th week we can work on this is the 15th week. And also you can do makeup makeup of the homeworks, labs. You still can make up, you submit you were lost at some point, but you still can have some point. I will post the details about them in the Blackboard. And the labs are already posted, I think. Yeah. Well, this is the 14th, this is for Friday's class, but now I'm not in the Friday. Yeah, but before you see this, you should know the rule about the homework and the labs, the makeups, how many points you can have. Yeah, you will lost some point, but you still can have the most point on those. But the makeup, we have deadline before. Sorry, I forgot the date. You check the Blackboard, okay? Yeah, by someday, by a day. Yeah, by a day before that. After that, I will not have time to give you credit to grade you those works. Yeah, after the exam, I need to grade the exam and then calculate the final grade and put the grading systems. They have a deadline of the whole university. So this one also give you a deadline. You check the Blackboard to see that. If you want to make up any of them, before that day. Alright, before that day. Okay, then we go to the review part. So first of all, for the coverage, cover the whole semester. Then you go to the Blackboard, you can see every week, every lecture, which part we covered. You can go over that, you can see all the coverage. And here I gave a summary just based on the textbook. Okay, check the key. We have chapter 2, the whole chapter, not the whole, chapter 2, 0 to 9 section, but no lesser section. Last section is about discrete time random signal. Do I have this? No, it's not covered in the final. Okay, so the first 9 sections. This is chapter 2. Chapter 3, we covered almost all the things except the last 3.9 section. And let me write it. Okay, chapter 2 from section 2.0 to 2.9, chapter 3 from section 3.0 to 3.5, and chapter 4 from 4.0 to 4.3. For the sampling theory, we just discussed how to take sample, what happened in the frequency domain, and how to reconstruct the signal from the samples. Right? We go over the first 3, 4, include the 0 introduction. So actually 3 sections. Right? This is chapter 4, and chapter 5. Chapter 5, the structure. Oh no, chapter 6 is chapter 6 structure. Chapter 5 is for the system. Some transform analysis of systems, and here we go over some of it, not all of them. I just write it down. We have section 5.0 from beginning until 5.2.2. 5.2.2. Okay, we have the stability, causality, what is the inverse system, and 5.3, no 5.3, 5.4, no 5.4. Okay, we have 5.5, the all-pass field, and 5.9, 5.6, the minimal phase. But it contains 3 subsections. We only go over the first one, minimal phase and all-pass decomposition. frequency. Yeah, just the first one, just 5.6, that is 5.6.1, just this. And then section 5.7, we have 5.7.1 and 1 to 3, 1, 2, and 3. Yeah, system with linear phase, generalized linear phase, and partial generalized linear phase systems. Right? Okay, so this is chapter 5. Then chapter 6 is the structure. We will also give some basic things. We have discussed some basic things. Block diagram, signal flow graph, different way to give the structure, and some direct form, right? Direct forms. Okay, so and the transpose form. So we have 4 sections. Chapter 6. We have sections 6.0 to 6.4. Yeah, .0, that is just the introduction. So every chapter, I put it here. If you are interested, you can read it to know more about the background, but you can skip it, is also fine. If you just consider for the exam, they are not important. Then chapter 7. Okay, chapter 7 is a filter design. We have this in the lab, so we will not cover this in the exam. Not covering the exam. And chapter 8 is also, we have a lab related in the, I think, the first or second lab. Right? Chapter 8 about the discrete Fourier transform. And chapter 9 is the FFT algorithm. FFT algorithm, I have one lecture to introduce it. If you are interested, you can try to design, to write your own program for the FFT algorithm, your own computer program. That's it. It is not included in the exam. Okay, so I put it here. 7, 8, 9. Chapter 7, 8, 9, not in the exam. Okay. Chapter 7, 8, 9, they will not be in the exam. Then let's go over the materials. We have studied several things. The first one about the signals. About signals. So we know the first one, how to represent a signal. We have three ways. Use the formula. For example, x of n equal to 1/2 to the n u of n, right? Like this, right? Like this, like a formula. And the second is a list of value. Like 1, 2, 4, 3, -1, and here is n equal to 0, things like this. And the third one is a graph. Graph. You have, for example, like this one, we have 1, 2. Oh, I need more space. Okay, I use a different one. Something like this. Right? You use a graph. Here's n. Here's x of n. Now you can use a graph to represent. So we have 3 different ways to represent the signal. The second one, we will have some change. Based on signal or several signals, we can have something different. So we have the operation of signals. The first type is like plus or minus or times, or divided, right, you can consider x of n plus or minus y of n, x of n times y of n, x of n divided by y of n, and also with constant, like a times x of n. Okay, so these are just the basic algebraic calculations. All right, and the second thing is scale and shift. And the shift on time. You have x of some constant, some k times n, like 2n, like x of 2n, like also include like this kind of thing, 2n plus 1, or like x of 3n minus 1. Yeah, not just the scale, but you can think this is all of these are similar, in a similar category. All right, you have some change in the time, right? Make some change in the time, and the shift, another shift. We have x of n minus some delay. Right? This is a shift. This is scale. Yeah, this is a scale, and these two are combined. Right? You have both shift by 1, shift by -1, and also you have a scale. Right? This is combined. This is just the scale, and this is shift, just shift, like shift by 4, right? Something like that. And the third one, this is an operation. Here's a signal. Yeah, this is also, all of these are kind of basically, right? Now we have a little bit advanced one, the convolution. Convolution. Am I good? Convolution. Convolution. So we have two signals. The notation is a star here. This star looks like similar as a multiplication in the computer, right? In the computer we use star for the times. But here if we put nothing between two signals, that means times. This is times. And we put star, this is convolution. And this definition is this one. It is summation x of k and y of n minus k, summation for all the k's. Okay. We can also calculate these in a table one, right? Table one. You have x and y. You have put some values. Yeah, some values. I just put this one represented values. Right? And like here's some x1. Here's some y1. Right? You have several y's, and then you do times them together. So like here will be x1, y1 times element by element. After you times all the element, like this one times this one, right? This one times this one times these, and put it in this area. Then do summation. You do summation, sum them together. You have some value here. This, okay, if I denote these as z of n, then here the summation along this line you have z of n. This is z of n. So you do the convolution, you can by this way, by table way. Usually this method works for if both x and y they have finite element, you can work by this way. If any one of them are infinite or both of them are infinite, yes, you still can work like this, but maybe it is not so simple as the finite length case. Okay, this is convolution. So this is an operation of signal. So from signal to signal. Result is also signal, right? Signal to signal. signal to signal. And the third one, this is the transform. It is also you will do some change from a signal, but the result is not a signal again. So this is from signal to a function on omega or z. Now we have two transform. The first one is a DTFT. This one is from signal to a function on omega. Is a x of n to a capital X of e to the j omega. Here, x of e to the j omega is the summation of all the x times exponential power negative j omega n, and n run from negative to positive infinity. That means for all the element x of n, we add them together, but each one you need a times exponential power of with power negative j omega n. And we can also have another formula to go back from capital X to lowercase x. This is 1 over pi times integral. Here we need one cycle. So we use negative pi to pi. If you use 0 to 2 pi, result would be same. And here is a capital X e to the j omega, and times e to the positive j omega n d omega. Right. So we have these two formulas. And this is a period. Period is 2 pi. So here we use one cycle for the integral about this x. All right. So this is the first transform, DTFT. And the second transform is Z transform. This is a start from x of n to a function of z. Okay, so we see their functions. This is a function of omega, this is a function of z. Then here capital X of z will equal to summation of x of n times z to negative n, and run from negative to positive infinity. So here just you can think this is just a replacement by replacement this part e to the j omega by z. Right. And we can go back. But go back, we do not have this formula. We still have a formula, but I never introduced it. It's very hard to use it. You need some knowledge about the functions on the complex variables, complex number as variable. So I just have this. And here you also need RC. Okay, then both case we need tables. We also need the partial fraction. Tables, when you calculate both sides for DTFT or the inverse DTFT, for Z transform or inverse Z transform, you need tables. And the partial fraction, that is just for the inverse transform. When you perform inverse Z or Fourier transform, you need to write the fraction in a summation as simple terms, right? Simple fractions, the partial fraction, and then use table. Okay, so this is a transform. All right, this is part 1 for signals. Then part 2 for systems. Basically, we have the type of system, right? We have several. We have like the causal, the stable, the linear, right? Causal, stable, linear, inverse do we have? A time invariant. Invariance. And 1, 2, 3, 4, 5. Yeah, we have 5 different kind of systems. Then consider then for LTI system. Now all the rest is about LTI system. We have, okay, yeah, remove this one. One is here. So the first one is represent, or we say description of a system. Here I mean LTI system. All right, LTI system. We have 3 things. We have h of n. Oh, we have 4 things. H of n. We have the equation. We have the frequency response. We have the transfer function. Okay, this is an impulse response. This is a frequency response. This is transfer function. Function or system function Yeah, system function or transfer function, same meaning. Okay. We have 4 different ways to describe system. Then you should know how to transfer from each one, from any one to the others. We have equation. You should know how to get h of e to the j omega, how to get h of z, and between them, right, how to do it. You just replace z by this one, or replace this one by z. You can transfer from both, right, from either side. But you need a condition. You need a condition. RC contain unit circle. RC contains unit circle. Then you can switch from transfer function to the frequency response. And also you have impulse response. Impulse response, here you do the DTFT. You have frequency response. Here you do the Z transform. You have the transfer function. Okay, so you need these. This is for how to describe a system. Then the input output. Input output calculate. Now you want to find output from input, right? Then we have 2 cases actually. So first one, we say A, regardless of initial condition. Then we have y of n equal to h of n convolution with x of n, or y of e to the j omega equal to h of e to the j omega times x of e to the j omega. Or we have y of z equal to h of z times x of z. Alright, and these 2, we need a inverse transform to get y of n. Okay, and you work in the frequency domain or z domain. Then by inverse transform, you get time domain result. Alright. And in a special case, if x of n equal to e to the j omega 0 n, then we have y of n will be h of e to the j omega 0 times x times the input. Yeah. And similar thing, if x of n is cosine omega 0 n or sine of omega 0 n. Now we have y of n will equal to magnitude of the frequency response times, I need more space, times here, okay, times this cosine of omega 0 n plus the angle of h of e to the j omega 0. We have this, or this cosine replaced by sine. Alright, yeah, this part is same, magnitude are same, just cosine change to be sine. If input is a sine, then here is sine. If cosine is cosine. And inside this cosine or sine, the inside part just same omega 0, same frequency times n, then plus the phase angle. Alright. Okay, so this is the first case. This, you can say this is a simple case. You just find output, doesn't matter what is the initial value. But actually, for different initial condition, the output will be different. So we have the second part, B, for the case when initial values are given. Now we have initial value. We have initial value, then the output. Now we have several different output. We have homogeneous solution. YH of n. There will be a summation like C1 lambda 1 to the power n plus C2 lambda 2 to the n until some P lambda p to the n. Now p the order of the system. This is the case lambda 1 do not equal to lambda I do not equal to lambda j. And if some lambda I equal to lambda j, lambda I equal to some, yes, some of them they are same. Now here's I do not equal to j. If we have some of them they are same, then we need a C1, like I said, yes, C1 lambda Ci lambda I to the n plus n times Cj lambda j to the n. Actually, lambda I lambda j are same, right? They are same. Then you put the n. If you do not have n here, these two are same thing, right? You just merge them. Then you do not have any new terms. You need a new term, so you just times n. And if we have more, like you have lambda k, then you need to add n squared times ck lambda k to the n. Okay. If these three are same, then you have more term, and so on. Yeah, if you have 2 or 3, you can work like this. You have 4, then you have more terms. Alright. And also if we have complex poles, so like lambda 1 equal to a plus bj and lambda 2 equal to a minus bj, then we have y h of n will contain just lambda 1, lambda 2. Maybe you have more terms, but for these two you have I will say a1 plus jb1 times lambda 1 to the n, and add a1 minus jb1 times lambda 2 to the n, and so on. Okay, so things like this, and all of these C1, C2, and CI, CJ, and A1, B1, they are arbitrary numbers. Arbitrary numbers. It could be any number. So actually, you have infinite solutions for homogeneous part. Yeah. Okay. So this is a homogeneous solution, and then we need a particular solution. Particular solution yp of n. Then this as in the part A. Part A, regardless the initial condition. So you can have that output for given input. You can have output. You can find output in this way. Okay, so use this one as the particular solution. And here, if you use the transform, and if you do not know the RC, then you can use any. Remember, for the Z transform case, when you perform inverse Z transform, different RC will give you different result. Then in this part, the particular solution, you can use any one of it. You pick any RC. Usually you have several different RC, right? You pick any one. You pick one. Then you can have your particular solution. But doesn't matter which RC. The final answer will be same. Particular solution will be different, but the final answer after you finish, you will have same thing. Okay. Use yp as in the part A. Then third part, we have all possible solution y or, which is a y homogeneous solution plus y particular solution. Because homogeneous solution, you have different choice, so this is all possible solutions. This solution is not unique. You have some parameter, they are changing, right, in this part. And then plug in the initial condition, the parameters in yh of n can be determined. Right now you have there could be some non-arbitrary number. After you have the initial condition, there will be some fixed numbers determined. Then we have y of n equal to, actually it is yr of n, but with fixed parameter. Right, you solve the parameter, plugging here, then you have yn. Okay, so these are the part how to solve the system. And then we have okay, this is a part 1, 2 for system. Then the first one represent, and the second one y is how to represent, and the order. I put them in different order. How to represent, then how to solve it. Yeah. One is represent, then second is input and output, calculate. Alright, and third one, we have the structure. Structure, we basically have two, we discuss two cases. One is for FIR field. Right? Second is for the actually it's for anything. For any cases, we have like all poles. Or post case, or both pole and zero. We have both poles and zero case, right? And we have two forms. Direct form 1 and 2, and the transpose. Direct form 1 and 2. Right? We have these 4 cases. FIR just one case. I still have two cases. You can put the Z delay here or Z delay in this side. Right? And this one, it looks like this. But the direction of the arrow and the location of the delays and the parameters are different. We have 4 different forms. Right? This is structure. And then third one is a mixture. You mix different part together, so we can connect the system by some subsystems. Use a parallel way to connect, or the cascade way. Okay, this is the structure. Yeah, this part is simple. You just know how to do it, that will be fine. And then we have the fourth part, the assembling. Or maybe this is third part. Yeah, the order. Maybe when we learn, which one we start. We learn assembling first, or we learn structure first. I forgot. Yeah, assembling method, assembling theory. Then we have x of n. It is coming from a continuous time signal with n times t. Okay. The basic in the time domain, it works like this. Here n equal to all the integers. Okay. And then in frequency domain, we have x of e to the j omega equal to 1 over t summation k run from negative to positive infinite. Here's the xc with j omega, but this omega is shifted by 2k pi and scaled by t. And we also have another function xs. This is continuous one. It is 1 over t. Yes, still 1 over t. K run from negative to positive infinite. This is xc of j. Now this is a capital omega, no scale, but we still have the shift 2k pi over t. Like this. Alright. We still have this one, xs of t. It is summation of xc of n capital T times the third of t minus nt. K run from negative to positive infinity. Now we have these 4 formulas. Yeah. This one is just give us the way how to take the sample. and these two are the function in frequency domain. And this is another function xs of t, which will be used in the when you restore the signal from the samples. And also to restore, we need a filter. We need a filter h of j omega or equal to something looks like this. Something looks like this, and here's a t, and this value. Now how to determine these? Okay, and r like this, like this. This is band pass. This is low pass filter. This is band pass filter. We have these two cases. Then which one will work? And what is value here? What is value here? You need find the graph of these two firstly, and then use this field to cut off all the rest. Just keep the original one. Keep the original Fourier transform of xc. To choose this t. Alright, here I do not give detail, but you should know the process, how to do it. Alright, the graph. This is important. Graph of these two. They are important. Alright, yeah, and actually related with it. And this one, you will know some value t, some value 0 for which case, for what kind of omega, for omega from where to where, right? You have omega smaller than something, larger than something. Like here is a smaller than this value, larger than negative of this value, that is low pass field. And this one you need two intervals, so omega will be larger than these, smaller than these, or larger than these, smaller than these, right? And you give the value t. Okay, so this is the sampling theory. Okay, then the 5 filters. For filters, we have different kind of filters, like low pass, like high pass, like a band pass. Right? Yeah, these are very, it's a very basically. Actually, do we have any problem just related with this kind of filters? No, but we have this in the lab, right? In the lab, you should know how to do this. And then we consider several different kind of filters. We have all-pass filter. We have the linear phase filter or general linear phase, and we also have the minimal phase field. Okay. So we have these three kind of filters. Then let me see. Yeah, we have some homework related with these. So you should for linear phase system, you should know what is the delay or group delay. You need to check whether it is really a linear phase or just a general linear phase, a generalized linear phase. And for all pass field, you can use it to change your system to be minimal phase field. To any field. If it is non-minimal phase, you can multiply by all pass field to to make the system to be a minimal linear phase. You should know how to do it, right? How to do it. So we have some problems. You check the homework. This is the homework. They give the different kind of problems and how to solve them, right? Yeah, this is a filter. And what else? Okay, it seems that's all, right? That's all. We have these 5 different parts. This part is after the midterm. The structure is also sampling structure, right? They are after the midterm, and then how to solve the system, how to describe the system, and how to describe the signal. They are coming from the material before the midterm. Yeah. Okay, that's all for today. See you next time. Bye bye.